Good evening. Good to be back with you again. We had to take 2 weeks off because of Hurricane Helene. Gary's studio was without internet. He's got solar here, but it doesn't work if we can't get out to everybody. Now, Charter has been kind of up and down. That's Gary's internet provider. And sometimes the Zoom is reporting that we're not going out HD. It's kind of intermittent. So if you see the quality kind of varying this evening, that's probably why. YouTube is showing full connectivity.
Remnants of Helene.
Yes, for sure. All right. So again, we want to welcome our everybody that's here, especially word to the YouTube students or people finding us online. If you're trying to keep up with us currently and we're not aware that you are doing that, please let us know so we can add you to the email list. The email list is only active while the class is running, so it'll be through the end of the year, basically. So let us know so we can give you the updates and advanced handouts and things of that nature. So this particular session part is Chapter 4, Part 2, and it's a little bit less challenging than the first half. So that's good news. There's even some easy stuff in this half. So I'm hoping that that'll work out to everybody's advantage. If we, depending on timing, we might be able to do a little bit of a demo at the end after the slide presentation. So we'll see how the timing works out. It's some material that's related to what we're going to be talking about tonight. All right, so this is what we're going to be talking about. These are the subjects. Resonant circuits is important because if we didn't have that, we wouldn't have ham radio. And the rest of it you can read there. We'll be going through all of that material. A little bit of math, but not too bad. The new things in particular are easier than what we saw last week. So that's a good thing. So we'll start right off with this slide, memory trick for reactance. I think we've mentioned this before, but if you can look at a capacitor, that can be a reminder that the circuit symbol reminds you of the formula, x sub c equals 1 over 2 pi frequency c. Here's the line, that's half the capacitor. And also the lines in the capacitor can remind you that the reactance is considered to be negative for the purpose of our calculations. Remember, we had positive for inductive and negative for capacitive, so the symbol might help you remember that. For inductors, the formula is just the inverse or the reciprocal. In this case, reactance and phase angle will be positive. It's negative for a capacitor. Now this is something that I sent out in my email, and I sent it out again this afternoon. And I sent something where you could print 4 copies. And for tonight, if you have one of these, I would encourage you to fill this out as we go. These are all on the extra class reference sheet as well, but the trick is to get this filled out so you know what it is you need to try to memorize. And then afterwards, tomorrow, for example, see if you can fill this out from memory and do it in, what did I say, less than 30 seconds or less than a minute for sure. And the good news is that several formulas have dropped out since the previous pool questions, so this is good news. So for tonight, just go ahead and fill these in as we get to them, and then you'll have a reference, plus it's on your reference sheet. So you can watch what we do and kind of know it makes sense when we're talking, but you really don't own it until you can do it on your own. So that's the reason for practicing this a little bit. I'll show you one that I wrote out over on the calculator cam. So I just scribbled off the formulas. I don't know if you can read my writing or not, but you go ahead and fill out yours as we get to these. But this is the idea. Go ahead and get a reference copy filled out, and then several times in the coming week, go ahead and see if you can reproduce this on your own. And the good news is this is all that you're going to need to know. And in some cases, there's workarounds where you won't even have to do the formula. I'm trying to package it all up for you as best we can. I also sent another handout this afternoon that was there's only 12 math problems in Chapter 4, both the first half and the second half in total. So those also can be used for practice. And in the previous email, which is probably 2 weeks old now, I suggested a challenge. Try to do the formula recall in 1 minute or less. Try to answer all of the 12 calculation questions in 10 minutes or less. And I don't care if you do it using the helps or you do it with the calculator, but you should be able to do that, all 12 of those in less than 10 minutes. And then go through the full ARRL exam review for Chapter 4 in 25 minutes and challenge yourself to see how you can do. I had a little form that I sent out where you could kind of keep score. There is one oddity in this chapter that it's question number E5D10. It's actually an antenna question that Gary will be covering in Chapter 9. It appears in the question list for Chapter 4. So if you see a question that asks about a conductor's as a conductor's diameter increases, what is the effect on its electrical length? So as that increases, the electrical length increases as well. But Gary will be covering that in Chapter 9. But if you see that question in the exam review, you'll kind of be able to know what it is. And I see the ARRL hasn't updated that yet. All right, resonant circuits. Jump right into this. Much of the magic of radio involves resonant circuits. Back in the good old days with spark gap transmitters and coherer detectors, they didn't have the ability to separate signals. It was quite a mess. I actually got to see some of that kind of equipment at the Asheville Radio Museum before the hurricane came through. Fascinating stuff if you ever get a chance at a radio museum. Okay, the magic at resonance. So what's happening here? And this will show up in the pool. At resonance, and voltage and current are in phase. Important concept. So remember capacitive reactance, X sub L. We plotted that on the y-axis. So some value is shown here. Looks like it's about around 300 ohms and some amount of resistance. At resonance, the capacitive reactance exactly matches the inductive reactance, and something magical happens. A poof. You might be able to hear the poof if you listen carefully. So what we're left with is just this. We wind up with the impedance being right on the x-axis. It's purely resistive. The capacitive and inductive reactance have completely canceled each other. And some major ramifications to that, as we'll be getting into. We saw this chart, I believe, in our last class. Resonance is the frequency at which the inductive and capacitive reactance are exactly equal. So what you can do, if this is true, you can solve this for frequency. If XL equals XC, you set those two formulas equal to each other, and then using magical algebra, you can come up with this formula, frequency of resonance, 1 over 2 pi times the square root of LC. In a little story, when I went to take my extra exam, I forgot this formula. So I spent about 10 minutes trying to trying to derive the equation from XL equals XC, and my algebra wasn't as good as I remembered it, and after about 10 minutes of fighting with it, my brain finally said, enough of this, here's, you can remember the formula now. So that's how I did it, and I got it right. And there's 2 pool questions where they ask us to calculate resonant frequency, and both of them have resistance in the as part of the problem. When that shows up, just ignore it. So circuit resistance does not affect resonance. So we worked a problem like this in the second session that we were together. This is, I said that there were 2. We worked the first one in week 2, and that I just kind of wanted to run through this one tonight as a review. So if you've got your calculators handy, let's see if we can do this one together. Find the magical calculator. All right, make sure that shows up well. So I'm going to first of all turn it on. The on button. Always press clear first. And here's our formula. Frequency of resonance, 1 over 2 pi times the square root of LC. Hopefully this is just going to be a review, but it's going to be different values because we're doing the other problem tonight. So use the fraction button and get the box over box with the top box blinking. We need to put a 1 in the upper part called the numerator, and we'll use the navigation diamond to get us below the line into the denominator. So we need to put in 2 pi with the number 2 and then pi. Now we need to get the radical sign in there, which is just above the x squared key. It's blue, so that's a second function. So I'll press second and then the x squared key, and you notice the display is lining up very nicely with the formula. That's how we try to do all of the questions or all of the problems, so that you have some feedback that you're on the right track. And then L times C. Well, L is 50 microhenries. That's times 10 to the minus 6th. So we're going to put in 50 EE for exponent entry. And then this is very important. Use the negation key, not the minus key. The negation key, minus 6. And now we have to put in the capacitance, capacitive reactance, times 10 picofarads. And pico is times 10 to the minus 12th times 10 EE, negation key 12, and then if we're lucky, it'll come out to 7.12 megahertz. 7.12 times 10 to the 6th is 7.12 megahertz. So hopefully that was mostly review, but with new values. I'll clear that and turn off the calculator. Any questions there? Anybody wants to yell? If you got a syntax error, it's because you used the minus key instead of the negation key. That's the biggest thing that people get trapped on there. Okay, so that was a review. Now we're going to get into two flavors of resonant circuits, series and parallel. They have different characteristics. They're both extremely useful in radio. So we've already seen that the frequency of resonance, the two types of reactances, inductive and capacitive, they're equal and they will cancel. Got a little diagram here. This is a frequency generator, RF generator. You see we've got a series circuit, resistor, inductor, and capacitor. The circuit at resonance is going to be purely resistive. Now here's one that might take some thinking. The phase relationship between the current through and the voltage across a series resonant circuit at resonance. The voltage and current are in phase. Remember we saw on the previous chart the little poof effect where inductive and capacitive reactance canceled and it became purely resistive. So that's kind of what this is saying. There's some pool questions where it feels like they put in a lot of complicated words, but if you just kind of read through what it says there, the in phase part I think will give you the clue that you need. And because the circuit is completely resistive, we've canceled the capacitive and inductive reactance, that makes this true, which is another pool question. The magnitude of the impedance in an RLC series circuit, as drawn, RLC, is approximately equal to the circuit resistance. Okay, now that might have you scratching your head a little bit because we've got three components in series here. Now the only way for the circuit to be purely resistive is if you hooked a wire up to the top of the coil and then shorted out these two components, L and C, you actually shorted them out, now the circuit would be purely resistive. And that indeed is what happens in a series resonant circuit. So you might be wondering, well, what good would that do? A little bit more, and hopefully we'll answer the question. So at resonance, again, we as I said, the coil and capacitor become a low impedance, they become a short. And we had a student, one of our past students said, well, if they become a short, well, why don't you just put the wire in there and then you don't need to buy the coil and the capacitor? Well, the reason that you don't want to replace it with a wire is because you get this effect of selectivity. And I threw some random numbers in here. At resonance, I picked 3.6 megahertz, and then I went above resonance and below resonance. And you can see that the signal is way, way down when you're off frequency. So that's the reason that that you want those parts in there. When you're tuning your radio, you want to hear this one, but neither of these. Now the maximum circuit current is at the resonant frequency. Now let's look at that and see if we can kind of figure out why that would be. When the circuit is not resonance, there's going to be some impedance across the coil and the capacitor, which is going to raise the overall impedance of the circuit. And you'll only get to the point of maximum current in the circuit when you have these parts shorted out at resonance. So hopefully with that explanation, you can see that the maximum circuit current would occur at the resonant frequency. Here's another amazing thing. Again, we're talking about series circuits. The voltage across the inductor and capacitor, because they're sharing their energy, they're storing energy and then giving it back continuously, they're trading it between one another. It's like gentle pushes on a pendulum. The push might be very small, but the pendulum has very large swings as a result of those pushes timed just exactly at the right time. So voltages across the inductor and capacitor may build to multiple times the source voltage. So if we're putting out 10 volts of RF out of the generator, and then you put a voltmeter across the coil or the capacitor, you could be seeing 100 volts at that point, which is really amazing. A couple of implications to that. You have to make sure that the parts that are spec'd will be able to handle the voltage for whatever the application is. You might be wondering, well, how in the world would I do that? Well, good for us. The radio manufacturers have figured that out. So within your radio at home, these factors have all been taken into account. And here's the same words put in the context of the pool question. Resonance can cause voltage across reactive components, meaning coil and/or capacitor, to be higher than the voltage applied to them. Seems like magic, doesn't it? Now we're going to talk about parallel resonant circuits. Now if you recall, see this curve here, the current through the circuit? It looks like a peak. Just opposite for parallel. Instead of a peak, we've got a dip here. And here's our parts, resistor, capacitor, coil, all in series. At resonance, they're equal and they cancel. But remember I said that we had a short circuit across the coil and capacitor for a series circuit? It's going to be a little different now. This circuit is purely resistive. So if we're asked what is the impedance of either a parallel or series circuit at resonance, they're both going to be purely resistive. And there actually are two pool questions that word it that way. And here's the equivalent right here. Magnitude of the impedance in an RLC parallel circuit at resonance is approximately equal to the circuit resistance. Okay, well, let's think about that for a minute. In order for the signal generator to only see the resistor, what has to happen over here? Well, we saw the short circuit for the series circuit. Here, these become an open. These components effectively disappear. Now, they're exchanging energy between the coil and the capacitor. One's charging and then discharging into the other, and around we go. But when that happens, they become invisible to the circuit, only at resonance. Another piece of magic, and you can see how the curve works here. So at resonance, the energy being exchanged between the inductor and capacitor will result in a large circulating current. In high power amplifiers, you have to be very careful, because even though we've got a tank circuit that's resonant at high power, it can actually melt the solder on the components. The current is so high. So again, our manufacturers have taken that into account. The only time you'd have to worry about that is if you were doing some home brew. And here's the way it appears in the pool. The magnitude of this is called a circulating current here. Magnitude of the circulating current within the components of a parallel LC circuit at resonance is at a maximum. So the circulating current is as high as it can go between these two components. One is feeding the other. It peaks at resonance. And as I said, these components disappear as far as the signal generator is concerned. So this is just opposite of the series case. The magnitude of the current at the input of a parallel RLC circuit at resonance is at a minimum. So as these components are, as you're below the resonant frequency or above it, you're going to have a current path through these components. At resonance, you're going to have no current path through these components. Therefore, that's what makes this true. The magnitude of the current at the input of a parallel RLC circuit, meaning here to here, at resonance is at a minimum. So since these are both pool questions, it's kind of important that you kind of understand the principle so that you'll get that question right. Now, what are the applications in radio for resonance and resonant frequency? Well, obviously we want to be able to separate different signals being received, the idea of selectivity. And some receivers are more selective than others. It has to do with the component quality and the design. You might remember Gary's mixer math, where you've got a signal coming into a radio and then you've got a local oscillator. You wind up with the sum and difference frequencies. Well, resonant circuits will select the frequency of that you need. It'll select the right frequency out of the mixer. So we want to maximize the transmit signal at the desired frequency. That's why in the good old tube type days, you had all kinds of knobs on the radio. You dip the plates and, peak the grids and dip the plates. Okay, I got it right that time. And sometimes you have to make these adjustments in a manual antenna tuner as well. That's all having to do with adjusting coils and capacitors to resonance. Filters, your audio and RF filters, depend on resonant circuits. An antenna can be viewed as a tuned circuit. People want to see the SWR low at a particular point in the band. Well, that antenna is acting as a tuned circuit at that frequency. Your multi-band antennas with traps, those depend on tuned circuits. And of course, antenna tuners. So just every place in ham radio, you'll find these things being applied. Harmonic suppression, notch filters, a couple more things. And right into some questions. So again, remind you of the 3-second rule. And it's kind of, I don't think I mentioned this before, but I actually looked on the internet to see if there's any basis in fact for the 3-second rule, meaning people say, well, if you drop food on the floor and if you can pick it up within 3 seconds, it's still safe to eat. Well, believe it or not, people have actually done that and counted bacteria growth, and there is some truth to that. But in But in our case, of course, we're asking people to pause 3 seconds before you give the answer. so that others can think about it, and folks that are listening online or listening to the recordings can pause and come up with their answer before they hear all of us. So, okay, that's the 3-second rule. We want to apply that here. So what can cause the voltage across reactances in a series RLC circuit to be higher than the voltage applied to the entire circuit?
Alpha.
Alpha.
Alpha. That happens at resonance. Thank you. What is the magnitude of the impedance of a series RLC circuit at resonance? And if you can kind of picture the diagram, that might help you answer it. Remember, at resonance, the L and the C disappear, leaving you with,
Alpha.
well, if the L and the C disappear, the only thing that's left is the
Delta.
resistance.
Delta.
Yeah, delta, right.
Yeah.
And getting things wrong is a good thing, believe it or not, because then you say, oh, well, what's the right answer? And you actually learn better if you occasionally get things wrong and have to kind of noodle your way through to getting to the right answer. Reinforces the information. So it is delta. What is the magnitude of the impedance of a parallel RLC circuit at resonance? You might remember that the answer for both parallel and series is the same answer,
Alpha.
approximately equal to the circuit resistance. Yes. What is the magnitude of the circulating current within the components of a parallel LC circuit at resonance?
Bravo.
Bravo. Yep, bravo. It is at a maximum. The coil and capacitor are just beating each other to death, exchanging energy between the two. Now, what is the magnitude of the current at the input of a parallel RLC circuit at resonance? And for this, you need to kind of remember the graphs that we showed you, or reason it out.
Alpha.
Alpha.
Well, it's actually alpha minimum, okay? That's because input parallel RLC circuit, yep. So this is the current coming out of the signal generator. You might have to kind of review this once or twice to get it firmly in your mind. What is the phase relationship between the current through and the voltage across a series resonance circuit at resonance?
Charlie.
Charlie.
Yep, the voltage and current are in phase, and this will remind you of a whole bunch of things we talked about with volt leading and lagging and all of that, but that goes away at resonance. Oh, okay, here's this one we did in week 2. What is I won't do this on the calculator, but see if any of you remember it or might know what it is. What is the resonant frequency with inductance of 50 microhenries and capacitance of 40 picofarads?
Charlie.
It is Charlie, and I'm going to give you 3 ways to figure these out. The first way, which I'd like everybody to be able to do at least once, is to use the formula and the calculator and give yourself the satisfaction of getting to the right answer. Okay, the second trick, for both of these questions, the answers are in a ham band, okay? So in this case, it's in the 80 meter band. The other one, I think it's in the 40 meter band. Okay, the third way of knowing which answer to pick, it's the answer that's closest to 5 megahertz, all right? So you've got 3 ways now you can get to the right answer. Okay, so using one of those tricks, or remembering what we just did a few minutes ago, now what would be the answer here?
D.
Delta.
Yes, it is delta, and that's the answer closest to 5 megahertz of all that are given, and it is in a ham band, 40 meters. I highlighted these in, I guess that's purple, because it'd be real easy to see the 7.12 and get the wrong units. So be careful of that. It won't look that way on your exam. So we're moving right along. We're doing really well. So Q, do we have any Star Trek fans amongst us? Remember Q on Star Trek? He's a pretty,
yeah.
pretty strange guy, okay? Well, Q is kind of a strange concept in resonant circuits as well. So, and it has the idea of how sharp a particular circuit is. So how selective is a circuit? If you've got a parallel or series resonance, is it extremely sharp or is it kind of broad? That's the idea of Q. The higher the Q, the sharper the selectivity. So just kind of get that, that idea in your head. Q you could think of as quality or quality factor, how pure the components are. The more pure the components are, meaning the less resistive effect, pure capacitance, pure inductance, the higher the Q and the sharper the selectivity. So just kind of get those broad concepts in mind, and it'll help. And here we've got a couple of cases here. Looking at the circuit over here, we've got an inductor, but it has some resistance. So the inductor might be pure, it might be a perfect component. Pure inductance, no resistance of any kind. Of course, we know that there's wire leads on it, and of course the coil is made out of wire, so it's going to have some kind of series resistance. The resistance tends to water down the purity of the inductance, if I can put it that way. So the higher this resistance, the less selective the circuit may be when it's combined with a capacitor. So in both cases, series or parallel, you can think of, these are the resonant circuits down here. There's going to be a resistor in series here, a resistor in series there. So it can be represented as ideal components in series with a resistor, and the resistance dissipates some of the stored energy. So the quality factor, or Q, tells us how perfect that part is. Is it purely inductive, or is it watered down a little bit by resistance? And of course it always is, a little bit. And there's some techniques to minimize that. So the ratio of how much energy is stored to how much energy is dissipated is really the definition of, it's the concept of Q, or quality factor for a part or a circuit. And the only way to increase the Q of an inductor or capacitor is by using components with lower losses. So an inductor, maybe it's going to be larger wire would help. Lower resistance, more inductance. So this is just background to kind of lead up to where we're going next. And we've already seen this, but not in the context of this pull question. Increasing Q in a series resonant circuit will cause internal voltages to increase. We saw that in a series resonant circuit we had voltages that could be much higher than the input to the circuit, but increasing the Q for an individual component will also cause the voltages to increase, because not as much of the inductance or capacitance will be damped out by the resistor, by the internal or series resistance. Now here we are showing the concept of selectivity again, and before getting into some of the technical details here, I think you can follow this idea. If we have a circuit, let's say it's this broad one here, let's call this a single sideband communication, okay? For single sideband, you'd want about a 3 kilohertz bandwidth. Let's call this really narrow one in the middle, let's call that about 150 hertz of bandwidth from this point to this point. That would be a very good selectivity for a CW signal. So grab that concept to start with, and then let's go through some of the detail. So bandwidth is the frequency range where the voltage or current is no more than 3 dB below the peak. It's also known as the half-power bandwidth. So we see that there's, here's the peak, and when we're 3 dB down from that, that's considered the break point for where we're going to define bandwidth. So 3 dB in terms of decibels, or whatever the voltage value here is 0.707 is the same thing as 3 dB down. So the half power bandwidth is the distance between these 2 points. Be certain, in case of a single sideband, you'd want this probably to be around 3 kilohertz. Called the half power or 3 dB bandwidth point. And here's the formula. This, I hope, doesn't look difficult if you're scribbling things down on that sheet of formula reference paper that we showed earlier. You can write this on your paper. Half power bandwidth is the frequency of resonance defined or divided by Q. There's a couple of questions in the pool that actually ask you to calculate this, and they're extremely easy. It's just the frequency divided by the Q, and they give us both of those. Higher Q narrows the bandwidth, makes it sharper. So you can kind of see that here. We're pretending that our CW signal is the most narrow one here, and on the graph it says Q equals 100. Our sideband case, 3 kilohertz, if you look at that curve, it says the Q is 10. So hopefully you're starting to correlate how higher Q gives you better selectivity. So higher Q narrows the bandwidth, makes it sharper. There's a couple of pool questions that are going to relate to this, so hopefully you'll grab that. So increasing the Q of an impedance matching circuit will decrease the matching bandwidth. Well, let's see if we can figure that out. So we know that if we increase the Q, it's going to become narrower. So if we increase the Q, it's going to decrease the matching bandwidth. Remember, we saw that in our hypothetical case here, the CW curve was at Q of 10, and sideband, or 100, single sideband 10. So if we increase the Q from 10 to 100, it's going to decrease the matching bandwidth. We're going to go from our 3 kilohertz to our 150 hertz. So it's an inverse relationship. And it says impedance matching circuit. Well, that could be an antenna tuner. It could be a circuit that's matching impedances between 2 stages in a transmitter. But the important thing is the relationship here. So how would we determine Q? Well, there's a couple of formulas for doing so, but generically, the way that you can determine it is, it's the bandwidth of the circuit's frequency response. Now, those sound like some really confusing words, but hopefully from what we've talked about here, they'll actually make a little bit of sense. The bandwidth of the circuit's frequency response, we saw that for our sideband case, 3 kilohertz. Well, that implies a Q, sharpness. So if we can look at the bandwidth of the circuit's frequency response, we can determine Q. And then we'll see how to do that mathematically. Okay, for a parallel resonant circuit, and in the previous pool, they made us, they distinguished between series and parallel. They made it a whole lot easier in the current pool by only giving us the parallel case. So that's the only one that I'm going to cover to avoid the confusion. And this is the formula. The Q of an RLC parallel resonant circuit is the resistance, R, divided by the reactance, X, of either the inductance or capacitance. Now, why do you suppose they say either the inductance or capacitance? Anybody have an idea? Well,
Because they're roughly equal?
they're equal, yes. Very good. Yeah, somebody's paying attention. That's good. Thank you for that. So kind of also notice in the formula that we've got reactance, X, and resistance. So you can kind of see how the resistance is kind of watering down the reactance. They both appear in the formula. There is a memory trick here. If you can't remember this formula, and one of our past, somebody was helping us with our class, was a paramedic, so he had all kinds of medical applications. So he said that a prescription is an RX. So if that little memory trick helps you, there it is. Q for a parallel circuit is R divided by X. resistance divided by reactance. So that's the concept. So now we're going to actually work a problem. We want to calculate the half power bandwidth. And here's one you can write on your paper if you haven't already. The half power bandwidth is the frequency of resonance divided by Q. Very, very easy problem to solve. Let's go over to the calculator. And I'll turn it on. Clear it. So it's the frequency of resonance divided by Q. So they're giving us the frequency of resonance is 7.1 megahertz, and the Q is 150. So that's going to be a fraction. So we'll press the fraction key. In this case, the frequency of resonance is 7.1. 7.1, but it's megahertz. So I have to, that's times 10 to the 6th, 7.1 EE, and it's positive 6, so I just put in a 6. And then I have to put Q in the bottom part of the fraction, the denominator. So I'll use the navigation diamond to do that. Put in the Q of 150, press enter. We get 47.33, which is 47 kilohertz. Oh, you know what I did? I forgot to update this. This is wrong here.
Points off for the teacher.
Yep. Gary's not going to pay me.
Never happens to me.
No, that's good. That's good. All right, so if we go back to the presentation, you'll see that I had it right there. So I hope I didn't confuse anybody too badly. I messed up on the card. That happens to be the answer for the other question like this. So that's how we do it. Frequency divided by Q. And in both cases, the problems that they're going to give us, they give us a frequency in megahertz, and then the answer winds up being in kilohertz. So, oh, I thought we had two of those. Looks like we only have one. That should make it easy. So here's some questions. Which of the following can be used to determine the Q of a series-tuned circuit? You might have to think about this a little bit.
C.
Alpha?
It is C, the bandwidth of the circuit's frequency response. So how much are we going to be allowing through in our selectivity, which is the bandwidth. So if we know how much we're going to be letting through, we can calculate the Q. What is the result of increasing the Q of an impedance matching circuit? As Q goes up, matching bandwidth,
A.
Alpha.
Alpha.
alpha decreases. Yep, inverse relationship. How is the Q of an RLC parallel circuit calculated? Your prescription is an RX thing, might help you a little bit here.
Charlie?
It is Charlie, resistance divided by the reactance of either the inductance or capacitance. So R over X. All right, this is the one that we just did, half power bandwidth, 7.1 megahertz, and a Q of 150.
Charlie.
Charlie, right. Oh, okay, this one we didn't do, but I was right. There are two pool questions, actually. Okay, so this one, if somebody wants to do this on their calculator quick and give us what you think is the answer. It's going to be 3.7 megahertz divided by 118.
Charlie?
It would be Charlie, yes. And again, we've got they give us the problem. It's a megahertz value, and it pops up in a kilohertz. Well, I guess these all do. That doesn't help you any. Okay, but you know how to do it by the formula: 3.7 megahertz divided by 118. Great. What is the effect of increasing Q in a series resonance circuit?
C.
C.
Charlie?
Internal voltages increase, right? Because if the Q goes down, that means there's more resistance. It's going to damp out that increase. So C is correct. Okay, we're moving right along. We're doing great. Things get really strange as we continue to increase the frequency. So we've got two fairly easy subparts of this chapter, and we'll get on to some demos if we have time.
Did you want to take a break at any time?
Yes, we will. I'll try to take a break about 7:30-ish if the time works out. So the skin effect in Q, that's the first one. Let's look at the diagram first. Here we've got a wire. So this is a cross-sectional area for a round conductor, and that entire cross-sectional area will be helpful if you're passing direct current through it. The fatter the wire, the more current you can carry. Now what happens when you move from DC to AC, the higher the frequency of the AC, there's a weird effect called skin effect, where the current flows on the outside of the conductor. So here's low frequency AC and here's high frequency AC. So you can see that we're getting less and less cross section of the wire the higher we go in frequency. Therefore, at a higher frequency, there's going to be more resistance here because there's less cross-sectional wire for the current to pass through. So with that as a backdrop, as frequency increases, the RF current travels in a thinner layer of the conductor closer to the surface. Therefore, the effective resistance of the wire increases because there's less of it. So at HF frequencies, 30 megahertz, let's say, it's only the outer few thousandths of an inch of the wire that current is flowing through. At VHF and UHF, we're talking a few 10,000ths of an inch. So if the resistance is becoming greater, the Q is going to be getting smaller, if you can tie that back to what we talked about. So for DC, you've got heavy battery cables for a lot of current. At higher frequencies, VHF, UHF, and above, if you could imagine a monofilament fishing line that was painted with conductive paint, that would be an effective conductor, because the section where the monofilament fishing line is wouldn't conduct anything anyway because of skin effect. Now there's skin effect. It has a practical application in something called a film capacitor. I've found a diagram of one here. A film capacitor is two conductive surfaces. Could be metal foil, and then a plastic film in between. So with the rising RF, skin depth decreases. We saw that on the previous slide. The conducting area decreases, driving up the component's resistance. Therefore, skin effect is the primary cause of loss in film capacitors. Here's a link down here. Wikipedia has just got a ton of information on all different kinds of capacitors, film, electrolytic, tantalum, if you care to dig into that some more. Very extensive article. Continuing our discussion about higher frequencies, we have parasitic effects. So what is a parasite? A parasite is something that's usually free and it's unwanted, okay? So the perfect illustration of that I thought was a mosquito. He's down here. So parasitic effects, unwanted capacitance or inductance. At VHF and above, parasitic effects become significant. So at higher frequencies, you really have to take this into account. But again, our radio manufacturers have done that for us. So the two tricks here, and pool questions, keep lead lengths short to minimize inductive reactance at these high frequencies. And short connections, that goes right along with short lead lengths. Short connections reduce phase shift at microwave frequencies. You might remember when we talked about the inductive and capacitive phase angles and so forth. If there's inductive and capacitance in the circuit, that will shift that phase angle, which is the equivalent to a phase shift. Very important at microwave frequencies. So how do we get self-resonance, you might be wondering. Well, here's an inductor, and in between each turn of the inductor, we've got some capacitance. So we have parasitic capacitance, parasitic capacitive reactance. And the reason I'm going through this is because the pool question is generic between inductors and capacitors. So that's why I'm going to kind of go through both of them here so you can see the connection. So an inductor will have a nominal value. Well, what's a nominal value? A nominal value is if you buy a 10 millihenry inductor, the 10 millihenries is considered its nominal value. Under ideal conditions, that's what it would be. But as the frequencies get higher, the parasitic capacitance is going to have a greater effect. So interturn capacitance is the parasitic characteristic that creates an inductor's self-resonance. And when we talk about self-resonance, it'll kind of act like it's supposed to at lower frequencies, but as you get higher and higher, the effect of the parasitic capacitance is going to become greater and greater. And at some point, it's going to switch from an inductor to a tuned circuit. It'll be resonant. And if you keep going higher in frequency, this inductor is going to be acting like a capacitor. Very, very weird. And if you don't know about this, it could cause some real strange effects in your circuit. Again, only if you're designing circuits or building radios, you need to take this into consideration. So self-resonance results from the combination, and here's where the words can get really tricky. Self-resonance results from the combination of a component's nominal, okay, by nominal we mean its rated value, and parasitic reactance. And the way they've worded this question, it could apply to an inductor or a capacitor. That's what makes it confusing. So self-resonance results from the combination of a component's nominal and parasitic reactances. Now let's look at self-resonance in a capacitor. Well, here's a capacitor, common. I showed you a film capacitor earlier that was just two plates with a plastic film in between. They're commonly wound, however, to increase the value of the capacitance and greater surface area on the plates. So what happens here, we've got a capacitor with a nominal value, 100 picofarads, and then we have the parasitic or inductive reactance due to the leads and due to, if it's a wound, if the component is constructed out of wound material, there's inductance there. So capacitor leads have some inductance. Capacitors that are made from wound foil have some parasitic inductance. And then I've repeated the same words here because they apply to an inductor or a capacitor. Self-resonance results from the combination of a component's nominal value and the parasitic reactance. So they worded this question where it could apply to a capacitor or an inductor. Now they do have, they talk a little bit about parasitic inductance in electrolytic capacitors. Electrolytic capacitors are typically used in power supply or audio frequency applications. They don't work well at RF. This is the construction. So inductance from the turns of an inductance from the turns of aluminum foil in an electrolytic capacitor cause them to be unsuitable at RF. So you might be wondering, well, why wouldn't that be true of a plastic or film capacitor as well? Well, the dielectric material is extremely thin on an electrolytic. It's just actually an oxide that forms on one of the plates against the electrolyte built in. So that's why, in particular, electrolytic capacitors are really unsuitable for RF, but they do a fabulous job at audio and lower frequencies. Another link here if you want to dig into it some more. And I'm not sure why the pool committee, maybe they felt sorry for us and wanted to give us some easy questions. So a couple of these ones coming up are going to be that way. And I think this actually would be a perfect time for a break before we get into component packaging at RF. So let's just kind of hold our place here, and we'll take a 5-minute break. Okay, we're back. Hopefully you did something fun during the break there, and we'll charge into some more easy material here. I think we're all done with calculations for tonight, so breathe easy there. All right, so what happens when we introduce radio frequencies, especially higher radio frequencies, into the equation for physical construction of equipment? Well, first of all, we're going to talk about a dual inline package construction. That would be this component here. So what is what DIP characteristic, dual inline package? 2 rows of connecting pins on opposite sides of the package, or DIP, like this. You can see how it would be mounted on a circuit board. There's actually holes in the circuit board that component goes through, and then it's soldered to the circuit board. So DIP is a through-hole device package. And they're not typically used at the really high frequencies, UHF and above, because of excessive lead length. So you're probably looking at this and saying, well, these don't look like very long lead lengths. But when you get into UHF and above, up toward microwave frequencies, these lead lengths do become very significant. So they don't use these parts there. So you can see we've got 3 easy pool questions about this. All right, so components with short leads reduce parasitic inductance and capacitance. So let's get rid of the leads. That would be a nice solution. We'll solve that problem, won't we? So there's a technology called surface mount technology that does that. I've got some pictures down here at the bottom. You've probably seen these on circuit boards. They're super, super small, and the component is soldered right onto the foil. So there's no lead length at all there. So here's some typical SMT components. And I don't know if you can see it, but this person's thumb, little tiny speck. So these can be pretty challenging to work on. If you enjoy building kits, a lot of the people who make kits will have the surface mount parts already soldered on the board for you. And the only thing you have to do is add the through-hole parts, making it a little easier. There are special tools that you can use to operate on these small devices if you wish to. So in terms of manufacturing, they normally will use some solder paste underneath the contacts of the part. That solder paste will kind of stick to the board. And if it's a component that's underneath the board, they use a little bit of glue to hold it in addition to the solder paste. And then the board is passed through. There's a couple of ways that they do it. One is that they'll just heat the entire assembly, which will melt the solder, make the connection. Or there's something called wave soldering, where they'll actually pass the circuit board through a wave of molten solder to establish these connections. Just a little overview of what it's all about. So, SMT components, surface mount technology, smaller circuit area, because if you've got these little tiny components, you can pack a lot more on a circuit board. Shorter circuit board traces, you don't have to go a long distance between components, and components have less parasitic inductance and capacitance. So this kind of sounds like an all of these answer coming up, doesn't it? There is one additional pool question, which I'll give you here. SMT components have the least parasitic effects above the HF range. So that feels easy, right? And guess what? We're right into some questions. What is the result of conductor skin effect? Conductor is like a wire. Remember, it just maybe a few 10,000ths of an inch on the outside of a wire.
Hey,
Alpha.
It is alpha, right? Resistance increases as the frequency increases because RF current flows closer to the surface. So the inner part of the wire doesn't get used at all. Why is it important to keep lead length short for components used at VHF and above?
Bravo.
B,
It is Bravo, to minimize inductive reactance. It might seem like for an inductor to be an inductor, it's got to be some kind of a coil. Well, actually, a wire lead all by itself has some inductance. And that's kind of what, that's why they want to keep these lead lengths very low, very short. Why are short connections used at microwave frequencies?
B.
It is B, to reduce phase shift along the connection. Just a different way of describing something that we've talked about in the past. What parasitic characteristic causes electrolytic capacitors to be unsuitable for use at RF?
C.
It is C,
C.
inductance, right? Because an electrolytic capacitor has got a huge number of turns in it, typically. And by the way, you haven't lived until you've smelled one that's blown up. I think somebody mentioned these make good firecrackers. You don't want to hook them up backwards. They smell bad and they make bad sounds. What parasitic characteristic creates an inductor's self-resonance? Now there's a...
Delta.
Okay, it is D. For an inductor, the primary parasitic effect is interturn capacitance. What combines to create the self-resonance of a component? There's one answer that you're going to be real tempted to say that's wrong.
Bravo.
It is Bravo, right? The one that you might be tempted to say is the component's inductance and capacitance, because you have to have inductance and capacitance to have resonance.
It's transaction.
Say again?
Or something that it was not meant to do.
Well, yeah, the focus really here is on the parasitic effect. So whatever the nominal value of the part is, what it's supposed to do, either inductance or capacitance, is combined with the parasitic reactance, either capacitive or inductive, to make it self-resonant. What is the primary cause of loss in film capacitors at RF? Think of the flat one that I showed you. Yep, skin effect. Mhm. Which of the following device packages is a through-hole type?
A.
A.
Yep, it is a DIP, dual inline package. Some of these other things are real, but not the right answer. Which of the following component package types would have the least parasitic effects at frequencies above the HF range?
Delta.
Delta.
Yep, they've given us some easy ones, and we're thankful for that. What advantage does surface mount technology offer at RF compared to using through-hole components? Read carefully.
Delta.
It is
Delta?
delta. Yeah, all of those things contribute. Yep, exactly right. What is a characteristic of DIP packaging used for integrated circuits?
Delta.
Delta.
2 rows of connecting pins placed on opposite sides of the package, dual inline package. And there can be a lot of things that are packaged that way. Op amps, for example, you might have 4 op amps in the package, or just all kinds of electronic functions that are put into one of these packages. Why are DIP through-hole package ICs not typically used at UHF and higher?
Charlie.
It is, yep, excessively linked. They don't look like they're very long, especially when they're soldered on the board, but surface mount is much shorter. All right, one more section to go, and then we'll be finished with the core material for the chapter, and then looks like we'll have time for my demo as well. So magnetic cores, here's some, this is called an air-wound inductor, a little hard to see maybe. And these are some other kinds of inductors that are wound around different kinds of cores. So what do inductors do? They store magnetic energy, creating reactance, inductive reactance. And how much? It's dependent on the number of turns and the core material. Different core materials will give you higher values of inductance for the same number of turns. And there's several different kinds of core materials. Air, I mentioned these are called air-wound resistors, or inductors rather. Air is relatively inefficient in terms of storing magnetic energy. But the reason that air inductors are used is that they have very high breakdown voltages. So you'll see them used very commonly in antenna tuners, high power transmit circuits and amplifiers and tuners, because they tend not to arc over very easily. But they're inefficient in terms of how much inductance they can provide. Magnetic materials increase the storage of energy and the inductance. If you can think of the magnetic material as focusing the lines of force in the inductor, that's what causes the inductance to increase. And of the different kinds of cores, ferrite will generally require fewer turns to produce a given inductance value. And we'll look at some other core types in a second here. Now there's a fancy term here called permeability. That's the core material property that determines the inductance of an inductor. So if you can have a material with higher permeability, you'll have higher inductance for the same number of turns. And there's three types shared with us here. Air is the reference. An air-wound inductor is considered to have a permeability of 1. Powdered iron and ferrite, two other core types, will have a permeability that's greater than 1. And then there's a real oddball here. If you take brass and put it into a coil, it actually decreases the inductance when it's inserted into a coil. So those are the three types.
Because of eddy current?
Is that because of what?
Eddy currents?
No, eddy currents we'll get to soon. Yeah, there's permeability is the property of an inductor that will, or a core material that will increase the inductance. There's something in brass called reluctance. It's another term, the opposite of permeability, that decreases the inductance. Don't need to know that, but just thought I'd share it. Core material in shape. This is considered a solenoidal form or shape. This is a toroid, resembles a donut. Here's, we don't really know what this one is because it's encapsulated, but it's important to select the core material carefully if you're building your own stuff. So different core materials will have different performance over a desired frequency range. And another consideration, as current increases through an inductor, you'll get to a place where it can't store any more magnetic energy. So powdered iron performs better than ferrite at high current. So there's trade-offs here in terms of what material you might want to use. In core shape, we've got our donut shape and our solenoidal shape. In a disadvantage of this kind of shape, the solenoidal, its lines of force extend above and below. So they can easily couple their magnetic energy to parts that are adjacent, which sometimes is not a good thing. So sometimes you'll see on circuit boards, if they're using these kind of coils, they'll be perpendicular to one another to minimize that. A nice advantage of a toroid, or donut shaped, is that most of the magnetic energy stays within the core, so you can space them together much more closely. And there's a poll question. Toroid cores reduce unwanted coupling by keeping most of the magnetic field contained within the core material, or inside the donut, if you want to look at it that way. So these don't couple to adjacent components as readily as this style. Then there's ferrite beads. Ferrite beads are your friend. And I've got one story. Gary might have a story too. But let's talk about what they are. First of all, it's a small core slipped over component leads, commonly used at VHF and UHF as parasitic suppressors at the input and output terminals of a transistor amplifier. Well, that's the one that they picked for a pool question, the wording. And there's another effect that is helpful to know if you do any kit building or design any coils yourself. When talking about toroids, one turn is considered a pass through the core. This would be 2 turns. So you can either count the number of times you pass through the core or count the inside passes. That's how you can be sure that you're winding at the right number of turns. Here's an example. Here's some that are commonly seen. A lot of you have probably seen these blobby things on the end of cables. That's a ferrite core, usually encapsulated, and its purpose is to keep RF, usually from the device you're connecting to, from radiating out into the air. Here's some other form factors. Here's a one that's wound. Then there's snap-on ferrites where they're hinged and you can snap them around a wire. So I'll give you my story first, and I think Gary has one too, but we'll do mine first. I had a keyboard that anytime I was transmitting, the keyboard wouldn't work. So if I was trying to type in a call sign in my logging software, I had to wait till I stopped transmitting before the computer would take the keyboard commands or presses. So I put ferrites on both ends of my computer. It was a wired keyboard, so I put ferrites on both ends, and it solved my problem. So that worked. And I know Gary used to operate out of a second floor ham shack, and I think ferrites are your friend too, right?
Yeah, my advice is don't put your ham shack underneath your antennas, which is what I had done. I had a roof tower and a hex beam antenna up above, and especially on 10 meters, the RF from the antenna would come down into the ham shack, and I had ferrites everywhere trying to eliminate common mode currents, which would cause, the keyboards to stop running, or your network connection, or your USB connection to go kaflooey. Maybe that's what's going on with Charter Spectrum tonight in our transmitted signal. Maybe we need to send them some ferrites.
Yeah, could be. Yep. Keeps RF where you want it, and keeps stray RF out of where you don't want it. So that's the concept. Magnetic cores, you've probably seen some of these on circuit boards. These look like IF transformers. So if you can just visualize a plastic soda straw with wire wound around it to make a coil, and then take a slug that's threaded and thread it into the soda straw, you'll have the concept of these kinds of coils. As you thread that ferrite material into the coil, it will increase the inductance of that coil. So as you screw it in, and inductance increases. I have seen some brass slugs in two-way radio equipment. Will reduce the inductance. And a little tip for you here: you always want to use plastic tuning tools, because if you're using a tuning tool and it's a metal screwdriver, a steel screwdriver, and you insert that into the core, well, that's going to mess up the inductance. So that's why tuning tools are plastic. So toroids, here we've got the solenoidal form on the bottom, a toroid, donut. The primary advantage of a toroidal core over a solenoidal, they concentrate the magnetic field within the core material, so they don't radiate. You don't have as much of a problem with pickup and the components surrounding it. And they also give you more inductance per turn than a straight solenoidal core. Can't describe the science behind that, but you see these are extremely popular in modern radios. One more little factoid. Here we've got something really hot going on. So powdered iron, we were talking about ferrite cores and powdered iron cores. two different core types. Powdered iron has the highest temperature stability of its magnetic characteristics. Some equipment runs at very high temperatures, so this becomes a factor. You need to know that. Now, what are some potential problems? Well, we mentioned that powdered iron will work better at higher temperatures, meaning higher current. So inductor saturation is caused by operation at excessive magnetic flux. That means you're putting current through the inductor that is in excess of what it can handle. You can only have so much of a field around the inductor, excessive magnetic flux. So that's caused by excessive current. And the ability of the inductor's core to store magnetic energy has been exceeded. Therefore, you'll get into inductor saturation. Now, you might wonder, well, why is that a problem? Well, a saturated inductor will behave in a nonlinear fashion, possibly causing harmonics and distortion. So I've got a curve shown here where this is the linear part of the curve, but if we're passing too much current, that will flat top the signal. That nonlinearity can cause harmonics and distortion. So these are all design considerations, and again, your radio manufacturer has taken those into account. Now, transformers, somebody mentioned eddy currents. We're getting to that here now. Now, transformers are also inductors. Makes sense? We've been talking mostly about RF frequencies, and two coils adjacent to each other will form a transformer at RF frequencies. We're looking at a power transformer here. So current induced into the core material is called eddy current. So when you think about it here, we've got here's some internal construction detail. We've got an iron core here, and then this is like if you've cut away some of these windings here, this is what you'd see. You'd have one layer that's the primary and one the secondary, surrounded by this iron core. The iron core improves the coupling between the primary and secondary, but at the same time, you see that this iron core is the equivalent of a one-loop coil that's shorted out. So we're actually inducing some current into the core as a result of energizing the transformer. So those currents are called eddy currents, and it's our goal, or the goal of the people that manufacture transformers, to minimize that because they waste energy as heat. So cores of inductors and transformers are sometimes constructed of thin layers to reduce power loss from eddy currents in the core. So here's an example or a picture of just the core. This is what's called an EI core. This looks like an E, and that's an I. There's all different configurations, but you'll see that they're kind of thin slices of metal, all sandwiched together, and that kind of breaks up the magnetic field. I think I've got, well, I'll show it later if we get that far. So this is what you need to know. Thin layers to reduce power loss from eddy currents. And a little bit more on, we're working up to something called magnetizing current. This is kind of a, it feels like it almost doesn't belong in this chapter, but it does have to do with inductance and inductors, so they wanted to cover it. You'll only find references to magnetizing current in generally power transformers and motor windings, so not so much RF. So current in the primary winding of a transformer with no load attached to the secondary is called magnetizing current. So if this was a power transformer plugged into 120 volts AC, there would be some current flowing, probably due to eddy currents, and the current that flows with nothing connected to the secondary of the transformer, that's what's referred to as magnetizing current. Kind of an odd concept. All right, into the questions. I think this is our last set of questions. Why are cores of inductors and transformers sometimes constructed of thin layers?
B, Bravo.
Bravo, correct. Yep, reduce power loss from eddy currents in the core. So that's wasted energy. How do ferrite and powdered iron compare for use in an inductor core? Remember, there were some advantages of one over the other depending on how you were going to use it.
C.
It is C.
Charlie, C.
Yep, ferrite cores generally require fewer turns to produce a given inductance value. What core material property determines the inductance of an inductor?
B.
B.
Delta.
Delta, yeah. I couldn't tell if B was B, Bravo or Delta, but it's Delta, permeability.
We should use a phonetic alphabet.
Yeah, that'd be a good application, absolutely. What is the current that flows in the primary winding of a transformer when there is no load on the secondary winding?
E.
Delta.
Delta, thank you for the phonetics, magnetizing current, correct. Which of the following materials has the highest temperature stability of its magnetic characteristics?
Bravo.
Bravo.
Bravo, powdered iron, yes. So what devices are commonly used as VHF and UHF parasitic suppressors at the input and output terminals of a transistor HF amplifier?
Charlie.
Charlie.
Yep, that's our ferrite bead friend. Ferrites are your friend.
Filters.
What is a primary advantage of using toroidal core instead of a solenoidal core in an inductor?
A.
Alpha.
It is alpha, right? Toroidal cores confine most of the magnetic energy, magnetic field within the core material. What type of material decreases inductance when inserted into a coil?
Bravo.
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 Yeah, that's brass, and that really is used. What causes inductor saturation?
Charlie.
Charlie.
Bravo.
It is Charlie. Operation at excessive magnetic flux, which happens if it's too much current for the inductor to handle. And then we're right at the end of this part of the presentation. We looked at this before, and hopefully you've kind of jotted these down as we've gone through tonight and have all of the answers. If not, they're all on your extra class reference sheet. And the challenge here is to memorize these and then try to reproduce this in less than 1 minute, which should be easy. 1 minute was our goal when we had the last set of pool questions. And there were about 4 or 5 more formulas than we have now. So that should be fairly easy. So work on that. And the other questions. I realized that when I sent out the email 2 weeks ago with the timed test challenge, I didn't put in the caveat that we hadn't covered the second half of the chapter yet. So if any of you tried to do that, you might have found it frustrating. But you should be able to do that now that we've been through all of this. So you should be very, very happy that we're through chapter 4 at this point. There was a lot of interesting and hairy stuff in here. This is where most of the scary math was. We have a lot of technical material to cover in the chapters that follow, but for those of you that were afraid of math, hopefully this is you now. You're all happy and jumping up and down. So what I want to do at this point is go over to the calculator cam and give you a couple of demos. This is called an LCR meter. Okay. L, inductance, C, capacitance, R, resistance. I'll turn it on. I think this was about $120. These are kind of handy, especially if you do kit building, because the parts that come in an electronic kit that you assemble yourself are sometimes so small you can't read them. So if you can actually measure the values, it can be helpful. So what we've done here, I've hooked the LCR meter up to an air-wound inductor. and it says that we've got 41.3 microhenries. And what I'd like to do is prove to you, bring this down so we can see it just a little better. Okay. What's going to happen when we put some ferrite material into the core of the inductor. Now, the meter doesn't respond instantly, but I'll put this ferrite core in, and you see what's happening here. It's increasing the value of the inductance. So at this point, we're at 63.9 microhenries. If I pull it out again, it'll return to 41.3. So that was about a 50% increase in the inductance. So that's the first thing I wanted to show you, to demonstrate that what we talked about really happens. Then the other thing I wanted to do, I didn't have any brass, so I can't show you that. The other thing I want to do is hook up a variable capacitor. So you've probably seen something like this in a radio. You don't have a small screwdriver handy, do you, Gary?
No.
Okay. We'll see if I can fake it here. All right. So get this up, hopefully where we can see it. So this is an air, what's called an air capacitor. Oh, I just happen to have a tuning tool. That'll work. Yeah, that's even better. So right now it auto ranged to capacitance. So it's reading this capacitor. It's about halfway. This up so you can see it, I hope. It's about halfway meshed. Widen this out a little bit. And if I crank it so that the plates are as far open as I can make them, like right there, now I'm down to about 9.3, 9-ish, it's jumping around a little bit, 910 picofarads. Now let me completely mesh the capacitor. And find the slot. Here it is. I'll completely mesh it. Now you can see that we're up to about 85 picofarads. So if you've never seen that before, I guess I'm just proving that as these things vary, it really does change. Got one more thing I wanted to show you. I ran across an inductor. Now this looks a lot like a transformer, right? But it only has 2 wires on it. So this is an inductor that would be used in a power supply circuit to smooth out the ripple of the rectifiers. So what I'm going to do here, and I was amazed at this. I almost don't believe it. But you can see that the entire part is, in fact, I think you can notice, I talked about the laminated core. Let me zoom in on this a little bit. It might be a little hard to see, little bit hard to see, but there's actually there's metal. This is done in thin layers. But back to what I was wanting to show you. This entire inductor, there's many turns here, so this is going to have a fairly high inductance value.
Can you zoom out so we can see it?
Oh yes. There we go. We're expecting a really high inductance value here. Notice what it's saying, 5.6 henries. That is a lot of inductance. Let's look at a couple of other characteristics. Capacitance, okay? Now remember we were talking about parasitic capacitance. Well, in capacitance mode, it's telling us that it's seeing 4.4 nanofarads, which is pretty small. But this is only operating at about 10 kilohertz, the meter. Switching ranges. Here we go. Okay, that's capacitance. It's not the one I wanted either. There it is. Okay, so there are so many windings of this wire inside the inductor that it's saying that we've got 0.468 kiloohms, so or 468 ohms, which is a lot of ohms for wire wound around an inductor, which is why the inductance is so high. So I just kind of wanted to show you that to reinforce some of the things that we talked about. All right, and with that, let's go to Gary's favorite part of the show here, class chat. We used to have there it is, the slide. So any questions or anything we can clarify?
How about the inductance loop at a traffic light?
I'm not sure how that works, other than the fact that the car over the inductance loop would change the inductance of the inductor and be sensed to switch the light. Anybody else know?
Yeah, the metal of the car is changing the permeability of the coil, and it's sensed.
Uh-huh. Okay.
Oh,
there-
the permeability. Okay.
Yep. Yep. There's another
Thank you.
there's another application of inductors. There's assisted listening systems in public buildings and theaters where people with hearing aids can actually pick up an inductive loop that's sending a signal to help people with that feature in their hearing aids hear better. So that's another application. You reminded me of that.
This
with
is
your-
what
Go ahead.
Tesla was trying to get with his power distribution.
Could be. We don't really know what Tesla was really trying to do there. Nobody's quite decoded that yet.
All right. Any other thoughts, comments, questions, observations? You feel better about Chapter 4 now, I hope? You should be very
Yes,
happy.
absolutely, thank you.
Yeah, you should be very happy about all of the things that we did not cover that are in that chapter. We just focused on the background and context related to the pool questions. So we were able to skip tons and tons of stuff in the chapter. Good. All right. Well, what are we going to do next week, Gary?
Next week is jam-packed with components, and we'll talk all about various pieces, parts that we use in electronics. And it'll be a jam-packed hour, but we'll get through the entire chapter. And I want to thank you all for bearing with us here after Hurricane Helene. Not only the 2-week delay, well, we had no internet at all, but even tonight, where our incoming internet stream was flawless, but it's our outgoing, which is the most important to you, that we were seeing some packet errors and some other things going on that we've never seen before. So I'm going to run some tests on our system again tomorrow, but I think they've still got some work to do.
Gary,
Yes, sir.
I'll be around if you need anybody.
All right, thank you. Yeah.
You're welcome.
Alrighty, y'all.
Give me a
Well,
call.
Thank you very much for everything.
we
Thank you, guys.
appreciate you being with us, and as we usually say, 73.
73.
We'll see you next week.
73.
Have a good night.
Appreciate y'all.
Thank you.
73.
Gary, just give me a call if you want me. All right, buddy. Goodbye.